This is Fred Sachs from the University of Buffalo. I'm going to show you here how to use QUB to do simulations of any state model you wish. This particular example is a 10-state model of a fluorescent indicator made from Gcamp from Dr. Torok from Clinical Sciences Research Institute, St. George's, University of London. Cube operates on states, and the meaning of those states is arbitrary. It could be dead or alive states. It could be anything you want, anything for which state models are appropriate. To simulate kinetics of a calcium indicator instead of an ion channel. Again, cube operates on states, and the meaning of those states is arbitrary. It could be dead or alive states. It could be anything you want, anything for which state models are appropriate. So this data actually comes from Dr. Tokol's paper that examined the kinetics of a Gcamp calcium indicator. So we're using Cube online for this. If you go to Cube, www.qub.buffalo.edu, especially if you spell it right, it works a lot better. And then we click on Cube Online, start Cube Online, and it's loading the program. Okay, this shows you a model that we've worked out that seems to work quite well. The rate constants are per second, such as the ones that have numbers on them. The ones that have L are ligand operated, and in this case the ligand is calcium. So this is 786 per second per micromole per second. The simulation here has a step of 1 micromolar for some period of time. To see how we can create from scratch, make a new model, I'm going to show you how. What we're going to do is go to File and say a new model. Now in Cube Online, both of these are models. You actually can have multiple models for different systems that interact. If you don't want to look at both of these models running simultaneously, you should X out the one you don't want. Okay, here, let's just begin. Left click creates a state, and all states of equal output we make in the same color. So black is dark state. Now we can change the name of that state. We can label it to be C for calmodulin. And the amplitude is, we're calling 0, that there's no fluorescent output from calmodulin by itself. If I want to put in a state now that's ligand dependent, I'll put in another state, And let's say this one is fluorescent. I'll make it a different color. Okay, I'll call this one bright. And I'm going to say that this one has a brightness of 54 units. Now, if I want to put in the rate constants between the states, I click on one state, then the other, and then right-click and drag and let go. Now, if I want to change this rate constant to be something or other, I can make it 10. And I want to make this return rate constant be slower, or you can make it whatever you want. I'm going to make the ligand, make it ligand sensitive by putting an L in here, down here. And in the simulation, we can specify what the ligand concentration is as a function of time. Just to keep you aware of the form of rate constants in cube, there's a pre-exponential term times a ligand concentration times the exponential of, in this case, the voltage dependence or the pressure dependence. So K2 has the units of inverse pressure, and K1 has units of inverse voltage. Now, if I want to do this simulation, I'll simulate the dose response curve. This is not steady state, but this is transient. It's defaulted to sampling at 1 kilohertz, and the name of the pulsed variable is L. The pre-pulse is right now set to 0.2 seconds, so that's from here to here. The pulse duration is 100 milliseconds, and there's one level. So you have the option here, if you want to put in finite relaxation times, you could set the input pulse to be filtered. Okay, and if I say OK, what happens? If I turn this one off, what happens? Aha. The other thing to realize is that in an option in the dose response is a little guy over here that says start at equilibrium. If you think that the states are in equilibrium, you can leave it on, and the program is smart enough to take all of those rates, calculate resting probabilities, and start from there. I think I'm going to start with calmodulin naked all by itself, so I'll turn that off, and it says the starting state is state 0, which was the first state I put in the model. And every time you change a parameter, Cube resimulates the data. For example, if I was going to change this rate here from 10 to 5, and I just hit enter, that is what you get. So here is the response, not unlikely, a two-state channel, but it takes time to get from pure unliganted through all the other unliganted non-fluorescent states till it gets to open and it fluoresces. Now why it should anticipate the closure up here, I'm not sure. You have to play with the model some more. But this is how you can use Cube to analyze any set of kinetics you like. when you can save the data, you can save the model as whatever you want. It's an OMJ model, and it's put, for default, it's put into your download directory. So if I call this model test, now if I go to my files and look in downloads, you'll see there it is, model test. And if you want to put this into a new model, just drag it over and drop it. Now we have two models. I'll erase this one, so there's only one model left. The other things you can do as far as laying out the model, so if I insert a state here and I want to move it, click again until it flickers, and then you can drag it a bit slowly, but you can drag it. And if you put another state in, you can again right click and drag to put in the rate constants, and then you can edit the rate constants. So the main thing is to have fun doing this. Once you get over doing one of these models, you will be able to do many more models. And they're simple to edit and simple to change, and there are all sorts of outputs that you can use. You can calculate first passage time if you like that one, or if you want to simulate and then you want to re-simulate the data, you can do that. And you can save or make new models. I'm annoyed at this Microsoft prompt. If I read it, I could have changed it so it didn't appear again, but it's a learning experience. So one of the things you might like to do is do some measurements right off the screen. So if you highlight that area, you find the visualizations over here. The duration is 2.1 times 10 to the minus 2 seconds, consisting of 21 data points. And the mean current during that time is 0.057 with a standard deviation of 0.103. And this is the minimum value in that window, and this is the maximum value in that window. Okay, have fun.